Dzień dobry, witam serdecznie.
Welcome everyone. The time has come. I hope you hear me, but it's not important. At the beginning, we would like to warmly welcome His Magnificence, Director of Lodz University of Technology, Professor Krzysztof Jóźwik, to open our today's conference. Your Magnifici, the floor, or maybe more accurate, the screen is yours.
I'm here. Sorry for the moment, but I tried to close that beautiful sound that's in my back.
Unfortunately, we cannot hear you.
Do you hear me? The audience, do you hear me? Please let me know.
We can see that your Magnifici is speaking, but unfortunately, there is some issue with the microphone. Okay.
Once again, I'm going to start the operation of my microphone. Do you hear me? Not exactly. The audience wrote that it is possible to hear me. So once again, I welcome you very much, very warmly at the Lodz University of Technology, but in a virtual way. Once again, we are in the situation that the pandemic is against us, and maybe against, but maybe it is for a part of you will be not able to participate in that beautiful conference. As far as MAFAB is concerned, I think that's a beautiful time if it is possible to discuss on mathematics. Mathematics, it is said that is a queen of all sciences, but for me as an engineer, it's a beautiful tool enabling me to operate every day in my work, especially some parts of the mathematics are very useful. Everyday life of everyone. If we want to start our operation, we have to consider almost everything as a part of our logical life. And due to that part of maths, it is possible to operate properly and considering positive ways and solutions for everyone. But you're here not to listen to me as an engineer. You are to consider to discuss some topics in maths. So once again, I welcome you very warmly. I wish you beautiful discussions, beautiful possibility to learn more on mathematics, to see beautiful applications, to consider beautiful solutions, and to use it in every day and at every day. So for all of you, beautiful time is something that I wish you very warmly. And I think it's a beautiful moment to say that the conference MAVSAP is open. So I give you the floor to consider the merit of that conference. Thank you for hearing me and to see you during discussion. Thank you very much.
Well, so again, sorry for the complications. Thank you, Professor, for your opening of the conference, as well as your assumption of the scientific patronage. And your speech has surely been very heartening for our lecturers and spectators who are here today because they are willing to learn, to constantly develop themselves, This is what our conference is all about. Now I would like to welcome the Vice Dean of the Faculty of Electrical Engineering, Electronics, Computer Science and Automatics to say a few words about our conference.
Thank you very much. Good afternoon, everybody. Well, it's my great pleasure to welcome all of you on behalf of the authorities of our faculty, the Faculty of Electrical, Electronic, Computer and Control Engineering. Well, mathematics is just beautiful in its simplicity and complexity on two hands. But actually, to understand mathematics well, you need to know how to apply it, know the mathematical tools, and that's what you are going to listen to about how to use different areas of mathematics in a real or even imaginary life. That's why I'm just looking forward. I'm keeping my finger crossed for all the presenters, and I'm wishing you fruitful debates to all the audience. Thank you very much once again, and let us start the MathUp conferences.
Thank you so much.
Okay, thank you.
So after our excellent guests make them speech, I think it's time to say a few words about itself. So here is Maria Rozpara.
And this is Patryk Goszczyński.
And we have the pleasure to elect on, in other words, to lead today's conference. So in a second, we start the prelegents with their presentation. And as to your guests, we would like to inform you to stay focused, stay tuned, maybe make notes to remember all the information which you can find out during this presentation, because at the end of today's conference, there will be a quiz and some kind of competition. So make sure to be by the end of today's conference and hear every prelegent with focus.
Okay, so now is the time we all have been waiting for. The first presentation is about to begin. So we warmly invite Aleksandra Kopyszczańska, a student from Krakow University of Economics, who will present a lecture about some Benford's law being used to detect criminal frauds, financial frauds, exactly. We are extremely happy to know this lecture and impressed that maths can be fooled and can detect the criminal crimes that even some people aren't. So, Aleksandra, the stage is yours.
Can you hear me?
Yes, we can hear you.
Okay, perfect. So please just a second, I will upload my presentation. Okay. Is this presentation visible?
Yes, we can see your presentation.
Okay, perfect. Thank you. So, hello everyone, my name is Aleksandra Kopyszczańska. I'm a second-year student at Krakow University of Economics, where I study corporate finance and accounting. And today I'd like to try to prove that math is not a science that can be fooled. Namely, I will discuss the concept and properties of the Benford's law. And since I'm closely related to the financial world, I will focus mostly on the application of the law in detecting financial fraud. But first of all, what is Benford's law? Also called the law of first digits, is the statistical phenomenon firstly observed in the 19th century by the mathematician Simon Newcomb. However, as it often happens in the science world, he wasn't the one who got credit for that, as the law was named after Frank Benford, the man who further developed the concept. And the law refers to the distribution of first significant digits in a naturally occurring data set. The word significant is very important here, as it means the first non-zero digit of a number. So in case of number, let's say 654, the first significant digit would be 6. However, in case of the number, let's say 0.478, the first number would be 4. And what is the law all about? Our intuition would tell us that having digits 1 through 9, the probability of each occurring in the as the first digit of a number should be exactly the same. However, Newcomb observed that it was not the case, as the leading digits in a collection of various datasets do not follow a uniform distribution, but are rather arranged in a decreasing manner, with 1 being the most probable and 9 being the least probable. The exact pattern is as follows. Probability of first significant digit d being equal to the logarithm with the base 10 of 1 plus 1 over d. Having calculated the logarithms, we get the following decreasing probabilities that you can see in the table. 1 with probability of 30.1%, 2 with probability 17.6%, down to 9 with probability of occurrence in the leading place of 4.6%. The graphical representation is as follows. We can clearly see the decreasing pattern in the probabilities. Now, let's try to answer the question where we can actually observe the law. Benford's law seems to be very counterintuitive and improbable at the beginning, yet it turns out that it applies to the most of large datasets. However, even small databases should at least roughly follow the Benford's distribution. But let's move on to the real-world examples. Firstly, we have the first digits of the numbers representing world countries' populations. As we can see, it is almost perfectly in line with the Benford's law. We can also observe it on social media. TikTok leading digits of 5,150 random posts also follow the discussed distribution. Another example, prices of American video games, which first digits form the Benford's pattern as well. Now, first digits of daily COVID-19 cases observable in the US over a period of a couple of months. And lastly, two financial examples. The first one is the Nasdaq Stock Exchange and its daily volume of shares for the past 10 years. And the second case, 20-year general ledger accounts. To briefly explain, the general ledger is a record of all past transactions of a company. As it's visible, leading digits of the transactions do create the Benford's distribution. And how the law can be helpful. As the few examples show, the Benford's law may be spotted in a wide selection of various real-world datasets. Thus, the obvious conclusion can be drawn that any significant deviation from the distribution can suggest either data manipulation or its incorrectness. In particular, some examples of the applications include financial fraud detection, something we will focus on today, for example, accounting fraud or tax fraud, election manipulation detection, and I'm talking here about the disparity of votes, assessment of correctness of compensations paid, let's say, by insurance companies, uncovering inaccurate numbers of COVID-19 cases presented by countries. We can see whether the countries recorded the cases correctly, whether they didn't understate or overstate the reported cases. Then testing the correctness of economic models, and basically spotting errors in numerous types of naturally occurring datasets. Let's see if the law works in real life. We'll look at a simple test that I conducted on a set of financial data using an Excel spreadsheet. The first step of my experiment was downloading trade transaction records executed by European governmental entities from the webpage Eurostat. Then 768 trade transactions were put in an Excel spreadsheet to do the analysis. How was it conducted? The first step was extracting first significant digit of each transaction using the function left. In the first place, we put the number and then 1. The next step was assigning, the next step was counting each first digit with the function COUNTIF. In the first place, we put the range of the previously extracted first digits and then digit of our interest. So 1, 2, 3, and so on. Then percentages were assigned to each first digit. The results are presented in the green table. 1 occurred in the first position in 27.68% of numbers, 2 in 16.54% of cases, and in a decreasing manner down to 9 with 4.43% of probability of occurrence in the first place. As we can see, the percentages are approximately in line with the Benford's distribution. It is even better visible at the chart. It suggests that the data that we analyzed was accurate and valid. However, we can ask a question. What would happen if someone wanted to hide something and manipulated the data, for example, by changing the values of the transactions or by adding non-existent ones? Once we conduct exactly the same analysis on the changed manipulated data as we did previously on the real ones, we get the following percentages that are presented in the red table. 1 and 19.10%, 2 and 13.33%, 3 and 19.23%, and so on. It is always better to look at the chart. Now we can clearly see that the distribution of manipulated data significantly violates the Benford's law, suggesting that something may be wrong with it. And actually, in this way, we can analyze various types of both financial and non-financial data. Once we observe some substantial divergences from the Benford's distribution, it should be the first warning sign that the data may be incorrect, and we ought to take a closer look at it so as to detect the sources of the errors. And slowly, coming to an end, let's have a look. Let's have a look at one of the biggest accounting scandals in history that involved the American energy company named Enron. The firm falsified their profits as well as results to hide the financial problems from their investors to ensure further funding. Once we look at their financial data from the year 2000, the anomaly is evident when we compare it to the Benford's law. And why is that? Because math can be fooled. Thank you very much.
Thank you, Alexandra, for your amazing lecture. And we really believe that it may actually prevent people from such crimes because they may get easily caught. So we invite now you spectators, if you have any question, you can ask them because we're actually a moment before the time. So maybe someone wants to ask something. Okay. We do not see the comments, so maybe we can. Okay, there is one. There is one.
Someone's writing.
Okay, I see the question why the first digits are not random. Actually, when I was doing my research to prepare the presentation, I found out that the question is still not answered. And it is one of the biggest mysteries in mathematics, why majority of data actually follow the distribution. It is still an open question. Okay, another question, where does the equation come from? I assume that the equation meaning the logarithm. So once we calculate logarithms of respective digits 1, 2, 3 down to 9, we get the decreasing probabilities. We can even get back to this slide with the equation, just a second. Oh yeah, it was here. So once we substitute d for 1, 2, 3 down to 9, we get the decreasing numbers, decreasing probabilities.
Okay, let's just wait a moment. We shall raise one more question. Okay, so
And there is one in the chat.
Just a second. Is this just a fit curve? Can I please ask for more details, because I'm not sure.
So maybe you can answer the questions in the chat box, and we can move on to the next person. And before we do that, we would also like to show you guys the patronage of our conference. So this year we have the honorary patronage of Młodzi Włodzi, the mayor of city of Łódź, Parlament Studentów Rzeczypospolitej Polskiej,
and the Ministry of Education and Science.
Yeah.
What's more, we have also the patronage from His Magnificency, the rector of the University of Technology, and also the media patronage from TVP, Żak Radio, also Życie Uczelni.
And also the Association of Women in Technology.
Yes. And now I think we can slowly move to our next presenter, who will tell us a little something about the artificial intelligence, machine learning. Now, by each day, we can see that computers and machines become even more powerful, and they are capable of even more abstract things and possibilities which we could never hope to think about like 5 or 10 years ago. But nowadays, computers are even able to create images, to detect if someone, to distinguish people based on their pictures. And more about this, we hope to be presented by our next prelegent. I hope, Krzysztof, that you can hear us.
Yes. Can you hear me, though?
Yes. The answer
Is the
is
sound okay? Last time it was a problem. Can you hear me, though?
yes, we can hear you.
Okay. So I will now share my screen. We will have the amazing presentation. Okay. We have a screen now. And can you see the presentation?
Yes, we can see.
Okay. So, welcome to my presentation about text-guided image synthesis with CLIP and VQGAN. So, today we are going to talk about a very neat technique that we can use to create images from text using artificial intelligence. So, the concept is rather simple. Let's imagine that we have a computer program that accepts some sort of a description of an image, like, for example, in this case, a glassed forest landscape image. And then we press a button, and then an image that is described by the text we put into the program is created by the computer. And it is not like Google image search, when we just search like internet for images corresponding to the phrase. We actually create those images from scratch using AI. So today I'm going to show you the mathematics behind such process. And the results can be really, really impressive. Like we can see here, those images are actually well created by the AI. And I would really put them on my wall. So yeah. And first, we have to frame our problem of image generation from text. And we, in fact, frame it as an optimization problem. So let's suppose that we have two functions. The first function takes some sort of a control input, which is a tensor. And this function, this generator function, turns this control input into an image. And by changing this control input, we can control what is on the image. And let's suppose that we have a second function which takes an image and a text and computes a dissimilarity between an image and a text. So for example, if we have a picture of a car and a text like the desert, for example, then the dissimilarity will be a very high value. And if we have, for example, a picture of a desert and the text is a picture of a desert, then the dissimilarity will be low. And what we can do is we can connect those two functions together into one function that takes the control input, generates the image from the control input, and compares it with the text we entered to compute a dissimilarity score. And so we effectively have one function that takes the control input and returns a dissimilarity score. And the problem of the problem of generating an image from a text is a problem of finding the control input z that minimizes the value of the dissimilarity. So this is an optimization problem. Now let's talk about those two functions a little bit more. So the function that generates an image is called is actually an AI called Vector Quantized Generative Adversarial Network. And well, unfortunately, this is actually a topic for another presentation. But in order to generate an images, what we actually need to do is only to create a rank-free tensor and then feed it into this essentially a convolutional neural network, and we get our image. And a tensor is just a sort of a generalization of a vector and a matrix to like high dimensional space. So we can, for example, have a single number, a scalar value, which is just a rank 0 tensor, a vector, which is a rank 1 tensor, matrix, which is a rank 2 tensor, and then many matrices stacked on top of each other to form like a cube of numbers, which is a rank 3 tensor. And then we can go to like arbitrary number of dimensions. So we generate just this cube of numbers, this rank 3 tensor, and we feed it into our VQ-GAN, and we get our image. And by controlling the shape of this rank 3 tensor, we can control the shape of the output image. In fact, we take the width and the height, and we then we multiply it by some upscaling factor, usually 16, around 16, and that way we obtain the size of the output image. Now, how do we measure this dissimilarity between the image and the text? Well, we use an AI called CLIP, which stands for Contrastive Language Image Pre-training. And this AI takes two inputs. It takes an image and a text, and it passes those two inputs through two neural networks. One is called an image encoder, and the second one is called text encoder. Those two neural networks, they take the input and create an encoding vector from this input. And those vectors are essentially just points in 512 dimensional space. And these vectors are going to have an interesting property, because if we compute the angle between those two vectors, then if the image corresponds to a text, so for example, we have a car and a picture of a car, then this angle between the two vectors is going to be small. And then if we have, for example, a picture of a boat and a text picture of a car, then the angle is going to be large. So what we can do is we can compute a cosine similarity between those two vectors, which is a cosine of the angle between the two vectors. And if the image corresponds to a text, then we have a high cosine similarity. And if the image does not correspond to a text, we have a low cosine similarity value. And to get the dissimilarity, we just multiply this cosine similarity by -1, and we get a dissimilarity. All right, so, well, now about the optimization process. Well, our task is to find z that corresponds to the lowest value of loss function, because this function is in machine learning, when we perform optimization, we usually call the function that we are optimizing a loss function. So it's like it's the value that we are optimizing is calling loss. And there are two challenges with this. So first of all, there is no analytical solution to that problem. And the second, so we can just put a text in and get z. And the second one is that for a 1024 by 1024 image, we have about 2 million dimensions in that space of. So this is a bit of a problem. However, there is a clever algorithm that can help us to find the value of the loss function. So let's imagine that we are in the mountains, and we are a hiker, and we are standing on top of the hill. In this analogy, the position in 2D space, which is our position in the mountains, corresponds to the input to the loss function, and the height of the landscape corresponds to the value of the loss function. And suddenly the storm comes, and we have to go to the valley in order to not get struck by lightning. And there is an additional complication because we have no eyes and we are blind. We cannot see the landscape around us, which corresponds to the fact that we have 2 million dimensions, and we can't see the loss function in any shape or form. So the actually rather clever strategy about going into the valley is to follow the direction of the slope. So if we take a small step in the direction of the slope, and then determine the direction of the slope again, and then take a small step in the direction of the slope, we can actually probably go to some lower place. Oh, sorry. We can go to a lower place, potentially a valley. So this technique is actually called a gradient descent, because we are following the gradient vector, which is which effectively is a mathematical way of saying a direction of the slope. In fact, it is on the right side we can see a function of 2 parameters that outputs a scalar value, and the blue vectors, they show the direction of the gradient vector. And if it actually points away from the valley towards the top of the mountain, but so we have to go in the opposite direction to that vector. And yeah, we essentially, so our optimization can be performed following the following steps. So we can first pick some random point in this space, in this 2 million dimensional space, and then we can compute the gradient, and we can then go in the direction opposite to the direction of the gradient vector, and we can then compute the gradient again, go in the direction opposite to the gradient vector again, and we can iterate it over again, and we will end up in some sort of a minima of the function. And this gamma in this equation actually represents something called a learning rate, which controls how large steps we are taking in the downhill. And on the right, we have the animation of this happening. But actually, we use a little bit more advanced algorithm than gradient descent. So the algorithm is going to look more like that rather than this simple formula, in order to provide faster convergence to minima and not get stuck so easily in the local minima. But it is essentially the same concept, that we use the gradient of the function to go to optimize it in an iterative fashion. Okay, so we optimize for z, and we get those images. Well, so there's another problem, and the problem is that the optimization works well, and it is creating an images that contains features that can fool the neural network into thinking that those that those images are close to a text. So for example, in this case of a desert, we might like synthesize some textures that kind of look like a desert, and it's enough to fool the neural network, and we get like the high similarity but low actual visual appeal of the images. So we have a missing ingredient. What we can do to solve this problem is data augmentation. So we take the image generated by the BQGAN and we randomly change it by applying random perspective, random rotation, random color changes, and crop. And that is making it more difficult for the optimization process to like find those small features that are fooling the neural network. In fact, we don't actually just have a single augmented image. We actually generate like 100 versions of this generated image. Each one of them is randomly changed, and we compute like the average similarity between the like the encoding vectors of those images and the encoding of the text prompt, and then we reduce it to the mean value, and we get our loss. So it's effectively just the average similarity between the like these augmented images and our text prompt, and this is what we get after 2,000 iterations with the augmentation. So it's impressive. We can do better. So nothing is actually stopping us from having multiple prompts. So instead of comparing the similarity between the generated images and our text, we can compare the similarity between generated images and multiple like text sentences and also images separately. And what that allows us to do is we can compute a weighted sum of the similarities between the generated image and different prompts. So we can control, for example, how much the optimization is favoring similarity to a given prompt. So for example, we can say we want to have some mountains, but we don't want too much mountains. So we can adjust the weight of the this mountain image prompt, and the higher the weight, the more mountains we actually get in our output image, because the optimization is going to favor the mountains if the weight is high. We can even have set weight to negative, and then the optimization process will try to steer the output image away from this prompt. Okay, so this is like a demo of this multiple prompt concept. So we can, for example, see the simple prompt forest landscape covered in snow. We can see a forest landscape covered in snow. Now we add an image prompt that shows the mountains, and now we can see that the mountains have appeared. Now we have mountains covered in forest covered in snow, and we can add another prompt covered in snow, and we can see that a lot of snow has appeared. So and by controlling the weight of that prompt, we can control how much snow is on the image. And since I have only so much time, here are some example results that I managed to create using this technique. We have a spherical computer, laptop made of lava, some table made of small rocks, the ball of lava surrounded by ice. So those are actually the prompts that I put into the AI, and this is what came out. And some abstract things work too. We have a journey to the center of the Earth, and it actually shows some caves. And the crystal cave also looks really nice. And I have put together a simple like a repository on GitHub, which contains the code that I used to generate this. I will also put some materials today there, some extra reading about the AIs and how they work in detail. Okay, so, and if you want to replicate this result, you will need about 30 gigabytes of graphic card memory to generate about 1024 by 1024 image. So I would recommend to do this in the cloud. But if you have okay, so no, okay, so that was I think it. So thank you very much for the presentation.
Thank you, Krzysztof. As always, very interesting about the machine learning and artificial intelligence. It's very nice to show what are the possibilities of modern computers. Do we have any questions from the chat? Let's wait a few seconds.
You can always ask those questions, of course, and The lecturer will respond in the chat box.
Okay.
Oh, someone's writing.
About on a GPU, about half an hour per image, 1024 by 1024 pixels. On a CPU, a few hours at least. It was ADAM. It's like a very good optimizer. We don't use the standard gradient descent because it gets stuck in like local minimas of the function. So ADAM was used. The code is actually, the implementation is from PyTorch library. Yes, it actually does. You can put like a little poems into the text input and it will generate images that correspond to those poems. It's actually quite creative, this AI. There is a limit about, I think it's like 200 words, and the sentence has to fit into 200 words. Yeah. Yeah, okay.
Thank you, Krzysztof. If there is no more questions, I think we can make another information for our partners. Yes. So, as always, many companies decide to partner and help in our conference by preparing some gifts or other form of supports. So in this conference, we have supports from Rossmann, Accenture, Commerzbank, Fujitsu, BSH, Woli, Twoje USG.pl, Wellfsedl, and Hycom. And in case of the gifts and the final prize from our conference, we present, those are the prizes for our conference, and the final prize for the winner of the best presenters is the sponsor, is from the
dean. From the dean.
Yeah, from the dean. The Trophium of the Dean of the Faculty of Electrical Engineering, Electronics, Computer Science, and Automatics. Yes. What's more, for the international conference, we have also special prize, which will be prepared by the director of International Cooperation Center, and also the gifts from the sponsor of our conference, as well as the gifts for the audience for solving our quizzes.
Okay, and now it's time to present you our special guest, the director of International Cooperation Center, Professor Dorota Piotrowska, who actually awards this special prize for English lecture.
Just wait a second.
Okay. You never stop walking. Okay, hello everyone. Can you hear me? Can you see me? Because I'm not sure if I am visible.
We can hear you, but unfortunately we
Hello?
cannot see you.
Hello, hello.
We cannot see you, but we can hear.
I don't know what's going on.
Oh,
Now we can see you.
Okay, good. Okay, can you hear me? It's okay with my voice and micro. I do hope I'm not muted.
Yes, everything is all right with your microphone.
Okay, okay, thank you. So let's get started. So, dear students, welcome to MATAF conference. I'm so glad that you are doing much more than just studying at the university. For those who are studying at IFE, you know that for me, it is very important to show you that like being student, it's much more than, you know, being taught at the school, okay? And such an event and participation in this kind of activities is very important for the development of your future skills. Right now, as far as I observed and as far as I see from my experience, employers are looking not only for the degree. Degree is important. However, they want to hire like creative people, engaged people, and people who are able to take different types of activities. This conference is almost fully carried out both by students, so I'm really proud of you guys, and I'm really glad that such, you know, activities and such engagement is right now a kind of specificity for our students. So this is really important. And sharing knowledge, it's also a skill which is important because, as you know, the world and our business environment is developing very quickly, and there are many like more and more inspirational things around us, and simply we don't have enough time to learn about all this. So that is why with sharing activity, sharing platform is that much important. So let me thank you one more time for your engagement, for being a part of this activity. And we really want Łódź University of Technology to become a place of useful learning, not teaching. Learning means that you can learn from teachers, but you can also learn in a very effective way from your colleagues, from students, from different activities, formal, informal, non-formal. So there are many options and many learning paths. So thank you once again for following all those paths, not just focusing on your studies, on your programs, because right now it's not enough. So you are already the winners, and I'm sure that in the future I'm in Madrid, and there are some students from Alcalá University passing by, so sorry for the noise. And so I am very proud of you, and I'm sure that in the future someone will appreciate this activity you are carrying right now. I wish you very fruitful discussions. As you probably know, there is also a kind of prize founded by the director of the International Cooperation Center. So, well, I do hope the best. See you tomorrow, guys. I do hope best performance, and I will be very happy to personally congratulate the winner of this international competition. So have fun, enjoy this time, and enjoy this sharing, experience, because as I told you, it's very important. I wish you a very, very fruitful discussion. Good luck. And I will be waiting for the winner at IFE building. Thank you very much.
Thank you very much for your kind word. And as you said, the soft skills are quite often forgotten in the engineering studies, but we can see that it changed. And as many said, soft is hard in reality, and those skills are also important and not so easy to acquire. But we hope that this conference and the possibility to present the ideas, to discuss the ideas, to prepare the abstract, the presentations, enable the students and also the participants to develop their skills in both soft and hard areas, which we hope will fruit in the future for them. Thank you once more for your kind
Thank you
words.
very much. Enjoy. See you.
Thank you.
Thank you.
See you.
So in a moment, you'll hear another extraordinary lecture presented by Tomasz Józefek from Łódź University of Technology. He'll tell us how not to be deceived by mathematics, especially statistics, and how not to fall into traps of it in our everyday life. Maybe you have heard already this phrase that Mark Twain used to say, but there are 3 types of lies. Lies, damned lies, statistics, so we better look out. Tomasz, it is your time.
Yes, thank you very much. This is not my presentation. Yeah, this one. Thank you. So good morning, everyone, and thank you very much for joining tonight's conference MathUp. You are all very welcome to it, and I will tell you how not to fall into probabilistic and statistical traps in everyday life, because as we always know, the mathematics is around us, and especially we almost every time encounter some probability and statistics. So without further ado, let me dive straight into my topic. And here is a little joke. Of course, all of you would catch that I will be not having 100% milk, the pure milk, if I add together 50 bottles of the milk, 2% milk. But the next mini stories, because I would like to provide you some mini stories, mini talks about some problems, it wouldn't be so obvious, and I hope you will see something interesting here. So let me begin with the doctor's paradox. And imagine this situation that we are going and willing, and we are wondering if we should take a very complicated operation that can improve our life, but at the same time, it may end up being an accident for us, a serious accident. And the doctor says that his operation is 95% successful. And probably in this situation, all of us would agree to be operated because this is the very high probability and probably nothing serious would ever happen. How about if the doctor told us that in average, 15 of his operations during a year are unsuccessful? Would you agree to be operated right now? Probably some of you would have some second thoughts about it, but let's assume that doctor performs 300 of this kind of operation each year. Then he said the same as in the beginning, that his operation is proven to be 95% successful. But there is also the third way he could present this information to us, that in his long, 20 years long history of being a doctor and performing this operation, it has been 300 unsuccessful operations. And it is still the same, that the one operation has an average of 95% of being successful. So these are the 3 ways of how he could provide us the same information, but we will be probably not so willing in this kind of knowledge, comparing to the first knowledge that I presented for you. So this was the first warming up story. Let me move to the Simpsons paradox. And of course, I didn't mean this very funny cartoon, but the graph has something in common. In fact, it shows us the corollary between variables. So let's imagine this situation, that it has been some survey where people were asked which dish tastes good and which tastes bad. And in this table, there are results of the men. And as we can see, men prefer dish A comparing to the dish B because this number is higher than this number. And this is the percentage of good in all of the responses. And we had also the woman asked the very same question. And if we compare at the same type, we also get that women prefer dish A to the dish B. And right now, if we add together the results from men and the results from women and write it on the table, we get that dish A is less preferred than dish B, despite that if we divided these two groups into the men and the women, dish A was more preferred than dish B. And this paradox is called the Simpsons paradox. And I really encourage you to learn something more about it because I only provided you here an example. And I will move to the next mini story. And this would be the story associated with being angry. Imagine this situation that you were on some social media, on Facebook, Instagram, so on, and you have encountered this kind of posts or /tweet that which says that as many as 30% of people who suffer from depression are women. And is it the right approach to this problem? Because in other way, you could also say that 70% are men. So was this a righteous anger? So what if I have started a campaign that aims to reduce the number of people who suffer from depression? I could do it in some certain way, but probably if I wanted to reduce the number of the men who suffer from a depression, because there is more men who are easier to help, because the more men are suffering from the depression, at the end of the day, I would get that 40% of people who suffer from depression are women. And it could mean two things. It could mean that the total number has raised or has fallen, because this percentage of women who suffer from a depression doesn't say anything about the total number. So we have to be aware of that while dealing with some information where we do not provide some total number information, but we are dealing only with some percentage of the total people or of the total, I don't know, money involved. So please be aware of that. And I will provide you now some examples from the real life. And it would be associated with the scale, because we can see these are the same charts, but this is the same function. It's exponential function, and this is the linear scale. We say the normal scale, which we are used to, and this is the logarithmic scale, where every increase is measured 10 times. So from 100 to 1000 is also the same increase in this scale as from 10 to 100 and from 1 to 10. This is called logarithmic because the logarithm of this function is presented here, if we were wondering. And there will be some examples from our television. And this is the chart. This is the healthcare expenses as a percentage of a total gross income of Poland. And we can see a lot of bad things here. But despite they are bad, they are not these are not any kind of lies, because it has everything written here. But we have the scale cut off, because here should be also 3%, 2%, and so on. And also 4 years are here missing from the 2016 to 2020. And we can also have this kind of situation here, that 1 year is missing and here 4 years are missing. So this is the real life situation, but we can see that it is not so obvious at the very first time that you have a look at it. You have to focus a bit, and yeah, you have to think what does it want to say. Another example would be some survey about the politician's view, and you can see that the percentage is bigger the bigger gets the head of this politic group. So this is the very funny one, probably my favorite. And we have also something about charts. This is the average female height, where also the scale has been cut off here, and of course people from India doesn't look like that comparing to the people from another countries. But we have to be also aware that the scale can go in the wrong direction, because we have the percentage of unemployed people here. And here the situation is that 2019 is on the right side and 2020 is on the left side. So actually the scale goes from right to left, not from left to right. And everybody should agree that of course, it is not what we are used to see, and we have to think a little bit before making some conclusions here. But not only in Poland are this kind of situation. Here is an example from the USA, and I could have some more of that, but instead, I would like to present some inflation. And this is a hypothetical country, and this is the inflation throughout the 7 years of it. And let me focus on the year from 2016 and 2017. One can say that there has been a decrease in the inflation, but how big was this decrease? And it turns out that the true information is there has been a decrease in inflation by 50%. Yes, because it's 2 times less than it have been in the 2016. But also, some other may say that there has been a decrease by 1% point. And people are also right, because 1% point is a decrease which has been noted here. But 50% and 1% point are equal because of this word point. And also we can do something like that in this chart, that in the 2022, we are here, the inflation was the same as 2021. So we don't have to really worry about nothing, everything is stabilized. But no, because the inflation itself just provides the information how, I would say, bad is the situation. So despite it's stabilized, it means that it's the same bad as it was. And we have to also be aware that some phrases as a growth of something may be also counterintuitive, because, for example, if we take into consideration years 2020 and 2019, we can say that there has been a decrease in the growth of inflation, because the growth was bigger here and less here. And it is also true because the growth is measured as a somewhat different than the inflation itself. Because despite it has been an increase in inflation, there has been a decrease in the growth of the inflation. I have also some expected value stories for you, and I would only end up saying that there are some games that have that we are more willing to pay for. For example, any bets that we make, they have less than 0 expected value. And not so many of us are so much willing to pay their bills, to pay their insurance bills. And as I saw, there will be some more presentations in the MAFAP conference about St. Petersburg game. And this is the game that you should go for it despite paying any money for that. So the casino could change $10,000 million and you should enter this. And this is very, very counterintuitive because in every bet you can win only not so many dollars. But yeah, I encourage you to explore this topic a little bit more. And also we have a birthday paradox. This is a good game to play with your friends in the bar or in the library. For example, how many people should it be so that the probability of two people that at least two people will share a birthday at the same day will be more than 50%. And it turns out that it only takes 23 people. And if we have a group of 50 people, then it is almost certain that at least two of them will share the same birthday at one day. And also there is some economics misunderstanding because, for example, this is the fact that cities with more police stations have more crimes. And so that could mean that there is a correlation between these two variables. And then in order to lower the number of crimes, we should lower the number of police stations. And it turns out that this is not how econometrics works, because the correlation is only from one to the other side, not in the two sides of that. And I will end up these mini stories by the one that is really fun, and it is 1 in a million chance. So, for example, let's assume that I have made it to the Olympic finals and I am participating in the 100 meters dash. And I will be participating with the best guys in the world. So my probability is really, really low of winning that thing because I mean they are very fast and I am not as fast as them. So the probability would be 1 to 1,000, I would say. That 1 in 1,000 cases I would win. But this never happens. You agree? But 1 in a million, it also never happens, kind of, but it happens. If it happens, then it is a miracle, and it's like you could write a poem about that. So what should I do? Then I must lower this probability of me winning 100 meters dash. So I would end up running blindfold and without shoes. And then this probability would be 1 in a million. And as we all know, 1 in a million chance happens because miracles can happen. And I would encourage you to live your miracle and don't wait any longer, and maybe not so to lower the probability of your success, but do something to increase that, or fail trying. Thank you very much for your time, and if you want to stay in touch with me, you can write or say. So thank you very much. If there are any questions, I will be willing to answer them on the chat.
Of course. Thank you, Tomasz. I have to admit your presentation is really showing math from the different angles. So I believe anyone, even someone who does not have interest in mathematics in everyday life, will get interested after it. So thank you very much again. Yeah, any questions you have, please ask in the chat box and Tomasz will surely answer. And we pass to another person.
Okay, so in case of coming to the next presentation, the next topic for many can be quite, probably not new, but very interesting topics which For once, it's very enigmatic, and for other, maybe scary. The topic of Bitcoin, topic which more or less we can say became more and more popular, and more people are aware of such, we can say, maybe technology, but or things. And today's presenters, Angelina, we hope will give you a little bit more information about this. We hope that you can hear us.
Hi.
Hello.
1 second.
One second.
Yes, that's my presentation.
Mm-hmm. Yes. So
Can
the
you see me?
screen is yours. Yes, we can see it.
Okay. I've taken an interest in the topic of the cryptocurrencies relatively recently when blockchain technology began to gain popularity. Although the technology was invented a long time ago, everybody began to talk about it only after appearance of Bitcoin. The technologies of distributed computing and decentralized information storage were introduced in 90s. However, the word blockchain became known only recently when Satoshi Nakamoto showed how these technologies can be used to create a new financial system. So in 2008, Bitcoin appeared, and with it, the history of blockchain development began. Blockchain is a secure database based on cryptography. All transactions are recorded in the Bitcoin blockchain. This blockchain is a giant ledger register like those maintained by banks for recording customer transactions. The information recorded in the blockchain cannot be changed. It's a very important moment. Blockchain is stored on many computers connected to the Bitcoin network. Therefore, the Bitcoin blockchain is called public. Anyone can connect to the network and download the blockchain, the complete Bitcoin ledger, on their computer. This network is distributed on peer-to-peer. The last means that in these networks, all computers or servers are equal, and there are no central management servers. A blockchain-based ownership records are becoming a much more reliable way to save property than a traditional safe or safe deposit box. This is provided by the use of elliptic curve digital signature algorithm. This algorithm is based on elliptic curve cryptography. A digital signature is impossible to fake, and its authentication can be easily verified by any network member. SCDSA includes two separate procedures for signature creation and verification. Each is a mechanism combining several mathematical operations. The first uses a private key to activate the transaction. The second one checks it using an open character set. There is nothing complicated about elliptic curves. Algebraically, such a curve can be represented as an equation. For A is 0 and B is 7, and this is exactly the version that Bitcoin uses. This curve looks like this. Elliptic curves have some useful properties. For example, a non-vertical straight line intersecting a curve at 2 points will always intersect it in a third point line on the curve. Another property is that if non-vertical line is tangent to the curve at one of the points, then it necessarily intersects the curve at exactly one more point. We can use these properties to define two operations on the points that make up the curve: addition of points and doubling. To add points P and Q is R, we draw a straight line through the points P and Q, which according to the properties of elliptic curves intersect the curves at some third point R dot. Then we find the point on the curve symmetric to the point R dot about the x-axis. the point R is considered to be a sum of P and Q. It is easily to understand by looking at the graphics. How would we add a point to itself? To do this, the operation of doubling the point is defined. P and P is R. When doubling the point, we draw a line tangent to the elliptic curve at the point P, which, according to the properties of the curve, should intersect it in another point R dot. The point R, symmetric to the R dot about the x-axis, will be considered the doubling point P. It's shown in the graph. These two operations can be used to define the scalar multiplication operation. R is AP, defined as adding a point P to itself A times. The process of scalar multiplication, as a rule, can be simplified using a combination of addition and doubling of points. For example, you can see it on your screens. Here, the 7p operation is divided into 2 steps for doubling the point and 2 steps for adding the point. As a result, instead of 7 operations, we only need to perform 4 operations. Actually, now you know everything about elliptic curves that is worth knowing about them. Now let's talk about finite fields. A finite field, in the context of a CDSA, can be considered as a given range of positive numbers. Any operation must be carried out within this range. In the result, if the result of the operation goes beyond this range, we do not get upset, but simply return to its beginning at the end of the range and continue counting as if nothing had happened. Thus, the result will still be inside our range, no matter how much he wants to get out of it. The easiest way to illustrate this is to calculate the operation remainder of integer division, or the modulo operation. For example, 7 divided by 7 gives 1 with a remainder of 2. Here we have a finite field from 0 to 6, and all operations modulo 7, no matter what number they are performed on, will give a result falling within this range. SCDSA uses not just elliptic curves, but elliptic curves in the context of a finite field, which significantly change their appearance. The same beautiful elliptic curve of Bitcoin, which is depicted above, but only defined on the finite field modulo 67, look like this. However, although it has become unrecognizable, the equations underlying this curve or its special properties have not changed at all. Now it's just a set of points where x and y values are integer between 0 and 66. Note also that the curve still retains its horizontal symmetry. The process of operation on points, addition and doubling, will now be slightly different visually. The straight lines drawn on this graph will now warp around the field as soon as they reach the magical barrier 67 and continue from the other end of it, maintaining the same slope but with a shift. Therefore, the addition of points 222 and 625 in this discrete version look like this. The turning line passing through these 2 points eventually ended up at the third point, 4739, and its symmetrical relative to the x-axis will be 4728. This is the point that will be the result of our operation. To use SCDSA protocol, the protocol such as a Bitcoin should select set of parameters for an elliptic curve and its finite field, so that all users of the protocol know and use these parameters. Otherwise, everyone will solve their own equations, which will not converge with each other, and they will never agree on anything. These fixed parameters include the equation of the curve, the value of the field modulus, and the base point that lies on the curve. The last parameter is the order of base point, which can be graphically represented as the number of times that the base point can be added to itself until a tangent curve becomes vertical. This parameter is selected in such a way that it is a very large prime number. In case of Bitcoin, these values are as follows. The numbers are not rising in demical, but in more compact hexadecimal form, familiar to programmers. This implementation is known as CECP 256K1 and is part of a family of solution of an elliptic curve in the field of finite fields proposed for use in cryptography. But who runs the process? All orders for transfer received in Bitcoin network are programmatically checked by servers in the network, which are called miners. During the verification, each miner checks if there is sufficient amount of money on the sender's Bitcoin address for the transfer, and the transaction record of the transfer is formed. The block of information is formed from a set of transactions to be added to the blockchain. But there are many miners who, from them, will write a block to the blockchain. To do this, Satoshi Nakamoto came up with an algorithm. The block will record the miner who first solves a complex cryptographic problem during the solution of which a certain number is searched for, which is in a spatial way connected with the checksum of the block formed by miner. The problem that miners solve to earn Bitcoin is postulate invert the SHA-256 hash function. SHA-256 is designated to be a one-way function which takes any data and converts it into 256-bit integer. One way means that it's easy to take data and compute the hash value, but it is difficult to take a given hash value and divide the data that would hash to that value. Bitcoin miners need to take data that represents transactions and hash it together with a seed value so that the hash is below a certain value. That value is adjusted over time to make it more or less difficult as miners join or leave. When someone succeeds, they broadcast that set of transactions to the rest of the network, and it becomes the next block in the blockchain. After the block is added, the miner who discovered new block is get a certain amount of Bitcoin for their contribution. In conclusion, I want to say that cryptocurrencies fully meet the challenge of time. They allow people to manage their own money. Even if you abstract from the course, the crypto will remain in your property in any case, if you manage and store it competently. No one will block it. The issue of Bitcoin is limited to 21 million. Bitcoins will not be released more than the limit to patch holes in the budget with a huge issue. This is the main advantage. It is a deflationary asset. Many people compare it with digital gold. This is one of the best investments when we talk about long-term perspective. Thank you.
Thank you very much. We hope that the presentation of our friend from Grodno was very interesting for you, and we hope that you have some questions. Something's writing in the chat. Let's wait. There's a question in the chat.
It takes many energy. They buy the most expensive computers to mine it, and it many time to get one Bitcoin.
Okay, so if you have any further question, you can ask them in the chat box. And now we have a mysterious topic. Can you speak math? But we are very much looking forward to knowing an answer for the question. If it's really possible to communicate with people all over the world using such a universal language as mathematics. So, two students from Łódź University of Technology, Rafał Bartosiak and Seweryn Koślicki, will try to answer a bit to that question. And the show is about to begin.
We hope that now you can see us.
And I hope that you can hear and see me now.
Yeah,
Yes.
1 second.
Great.
We wait for the other.
Okay, now you could be.
Now
both
both of you should be able to turn on your cameras. Great.
Hello, good afternoon.
And I hope you can see the presentation right now, shared by me.
Yes, we can see.
Great.
So let us begin. 67.1%. This number represents the number of Polish population who admitted to knowing at least one foreign language, according to Eurostat research made in 2016. However, some people would risk the statement that almost 100% of Polish population is in fact capable of speaking at least one foreign language. Which one, you would probably ask yourself? The answer is mathematics. The controversial matter of whether mathematics can be considered a language will be the topic of our today's presentation that my friend Rafał Bartosiak and myself, Seweryn Koślicki, will have pleasure to deliver to you. We are going to start by a short reminder of a language definition. Then we check if it could be applied to mathematics. We'll follow by presenting you the argumentation of both sides and finalize it with short conclusions. Now giving the floor to my colleague Rafał.
So to start our considerations, let us remind you what the definition of the language actually is. Collins Dictionary provided us with a statement that language is a set of written symbols and sounds that are used for a given group of people to communicate between each other. We may also approach to define language a little bit differently. One can say that language is a set of components that are used to construct the language. So, as I said earlier, we may also say that language is a set of written symbols which can be constructed into vocabulary. And hence, it is logical to say that this vocabulary needs to have some meaning. Because, well, we can try to come up with a word that has no meaning, but it won't rather find any use in our everyday life. Also, we have grammar and narrative, which are a set of rules that need to have each language, so that it can be used by people. And even though it is often a burden for school pupils to learn it and to memorize it, we need it to fluently use given language. And of course, last but not least, the users, the people who communicate through it and maintain it so that it is not forgotten. And now you may ask us, these definitions are very, very linguistic. And how can we compare mathematics to it? Well, apparently we can. First of all, we also have vocabulary in mathematics. So first of all, we have nouns that are mainly numbers, geometrical shapes, infinity or pi. What's more, we can do some actions with those nouns, which are verbs, such as trigonometrical functions, check the equality, or as simple operations as multiplication or division. And as I just explained, all of these have their own meaning. So just like with words in language, we have meaning in words for words in mathematics, and we also have a set of rules that we have to follow in mathematics. So first of all, we are reading mathematical expressions from left to right. Sometimes we have brackets that, just like in this mathematical tautology, first we analyze logical and after we analyze logical or. And of course, we also use unwritten rules for defining concepts such as unknowns, functions, or Greek letters. And it is much easier for any person to use those rules, because we probably remember from school that when those were mixed up, there might have been some confusion. And as you may already see, one of the users, we also have the users of mathematics. The great mathematicians helped us organize and came up with conclusions and concepts so that we people can use it in our everyday life and use it fluently and easily.
No. Starting off the argumentation for math being a language. Imagine two Polish engineers meet to consult a technical project. However, both of them gained their technical degree in different non-native language. Hence, they did not possess technical vocabulary in a shared native language. Now, although the specific technical nomenclature cannot be used, we must remember that where two is two in English, but zwei or dwa in other languages, two, as you can see presented on the screen, is still two in every other language. And this creates a solid ground for common understanding and communication, and makes it possible to communicate on a reasonable level. Using math equations, signs, and theses, one can easily express most of the technical details of a topic in an understandable to another specialist way. Not only is math a universal tool to communicate with others who possess the ability to use it, but similarly to languages, math can be translated into other languages. In the same way, we can translate word jabłko to apple. We can translate mathematical expressions to, for instance, our mother tongue. For example, given integral sign to integral, derivative, or a matrix monster. And that's what everyone has been doing so far on mathematical classes, which everyone attended, when reading out loud a solution of a task or trying to solve a text task. So what actually happens when trying to solve a given task, like Julia had 2 kilograms of apples, she had eaten 20% of it, and out of the half of the remaining made apple pie. How much does she has left? What happens here is the translation of conventional language to mathematical notation or mathematical language, because it's way easier to solve that using aforementioned signs. Now, to read the answer to the class, we need to once again retranslate the mathematical notation or language to our mother tongue, being, as you can see on the screen, that Julia has got only 0.8 kilograms of apples left. Now, moving on to a part that some of you may already consider cliche, namely that somehow people throughout the history have managed to develop a tool that can describe surrounding us world. We can observe it everywhere. That is, for example, waves in the ocean, planetary orbits of shape of honeycomb. And while we can get to understand almost any phenomena using only conventional language, conventional words, it is extremely difficult to work with and dig deep into complex models without the additional new language called mathematics. Mathematical expressions, formulas, graphs are widely used to express dependencies, correlations, or the level of magnitude of certain phenomena. We could say that force is strictly correlated to acceleration, or we could say that increasing the temperature increases the particle's kinetic energy, and possibly imagine those things. But how exactly could we be able to predict existence of Higgs boson without mathematics? Isaac Newton has asked now a famous question. If the apple falls, does the moon also fall? And this problem couldn't have been solved for quite a while until Isaac Newton managed to develop a new way of description of the problem, namely a new language, which nowadays we know and call calculus.
And as in any discussion, we will always find speculators. And we are aware that for now we showed you only arguments for the statement that mathematics can be considered language. Now let's focus on those against this statement. And to start off, biology. So according to a study of Marie Almary and Stanislas Daen from Université Paris-Sud, mathematics and language do not correlate biologically. In the research, they asked mathematical professors, as well as those from other fields of science, to solve and examine mathematical expressions and some others. So it was already well known before that for language cognition, left hemisphere of the brain is responsible and is activated. However, according to the results, for mathematics, it is rather more complex. And even though, as you may see on the very advanced diagram here, some of the parts may correspond to left hemisphere, according to the results of the study, it is rather not connected. So we may say and conclude that language and mathematics are connected. However, apparently our brains agree to disagree. Earlier, my co-presenter Severin showed you a situation when two engineers made research in some different languages. And he told that mathematics allows for them to communicate easily about their result and research. However, to actually use it and speak through it, we need a somehow language booster so that we may express what we actually want. So, for example, when I say I squared is equal to -1, I just used English, even though I spoke using mathematics also. So there might be some confusion. And well, apparently mathematics seems to be rather written, not spoken, whereas normally languages are both. Next, we all know that linguists are the ones responsible for studying languages. They study all the languages in the world, and they study their roots, how they are organized, or their alphabets. And if we stick to our conclusion that mathematics can be considered a language, well, the question can be posed: why do they not study mathematics also? They should also try to derive how, for example, we write different symbols, or how mathematics is organized. However, the question is not for me to answer. I leave it for you.
With all the arguments presented, we would like to leave you to your own thoughts. We hope that some of you will try to reflect on how differently can math and the role it plays be perceived. For those who got interested and would like to dive deeper into the discussion, we recommend checking up Reddit or Stake Exchange, for instance, as there are immense debates concerning today's topic. But if you are still looking for a straightforward answer, we have asked already for you the greatest specialist in all fields, who gave us short yet exhaustive answer. And we would like here, thank you for your attention, and we would be glad to answer any of your questions.
So thank you, Rafa and Severin. And this is really a thing. Math can be a true language. We're very excited to hear your presentation, and we really enjoyed it. And we also hope everyone did too. So yeah, if there are any questions, please ask them in the chat box, and we will pass to another participant.
Thank you very much. Thank you.
Okay. Okay. So now we can go to our next presentation, which will be presented by Agata Kmiecik from the Lodz University of Technology and Edyta Gilewicz from University of Gdańsk. And the topic is, can mathematics predict your future? Well, when we think about the mathematics, we probably mostly associate math with logics, with something which can be proved with either yes or no, or some more sophisticated, but still logical answer. But as we can see, maths can be associated also with other disciplines, and we hope that Edyta and Agata will be able to tell us more and maybe take interest, or for sure take interest of all of us. We hope that now you can show yourself to us.
Yes.
Good afternoon. My name is Edyta Gilewicz.
And my name is Agata Kmiecik.
And today we are going to be talking about the mathematics of astrology. At the beginning, we would like to mention the most important issues which will be discussed in our presentation. In turn, we will speak about definition of astrology, horoscopes, great circles on the celestial sphere, horoscope, zodiac, houses, and numerology. So let's start with the definition of astrology. Astrology is the belief that there is meaningful relationship between the position of celestial bodies and human experience, and that we can systematically determine this relationship. I would like to point out that astrology is something completely different from astronomy. I know that many people confuse these two things. However, astronomy is a scientific study of the universe, while astrology is some kind of divination.
So astrology deals mainly with projective geometry, and it means that distances to celestial bodies are inconsequential. What's important is their relative positions on the celestial sphere, so only the angular differences from the Earth matter. To obtain some graphical idea of the celestial sphere, now I'm gonna tell you a little about the most important great circles on it, and then we can move on to the next slides. So a great circle is a circle on a sphere obtained by intersecting the sphere with a plane that passes through the center of the sphere. There are certain important great circles on the celestial sphere. For example, as you can see on the picture, there's the celestial equator, and it's here, which is a circle that cuts the celestial sphere into two equal parts. With respect to the poles, we have North Pole and South Pole. Another example is ecliptic, and it's showing the annual path of the sun. The plane of this great circle always makes an angle of 23.5 degrees with the celestial equator. And this tilt is of great importance because it's responsible for the seasons on Earth. As many of you may already know, to cast a horoscope, an astrologer needs the date, place, and the exact time of birth. This information is needed for the calculations to construct the individual's horoscope. A horoscope is nothing more than a map or a diagram of the various planets' positions at any one point in time with respect to the Earth. And now I would like to show you some simple way to predict planetary positions at any given date. So we will need a diagram like this with orbits marked in fractions of the orbital periods. On each of the orbit, the point labeled 00 shows where the planet will be on the 1st of January 2000. Likewise, the point labeled 0.1 shows where the planet will be on 1/10 of an orbital period later, and so on all the way around. Here we have a list of orbital periods of few planets that will be essential for our calculations. The first step is to calculate the number of days from the 20th of September 1964, because that's the date that I've chosen and I've prepared the calculations before. We'll call this number D, and we have 35 years, 1 month of 30 days, 2 months of 31 days, and 10 days. This number has to be negative because my chosen date is before the 1st January 2000. And if I had chosen, I don't know, yesterday, the number should be positive. Now I need an orbital period P listed in the table on the previous slide, and I forgot to mention, but I will be calculating the position of Mars. So I will need this number, and I have to divide my D by the P, and the result is minus 18.76. My R is negative, as you can see. So I'm taking the integer part of the result and add 1, and I have 19. I'm calling the result S. Now I have to add R and S, and I have 0.24. The F value is just the fraction of the planet orbits it has completed by my chosen date. Using these values, I will later mark the planet's position along its orbit. I've also done the same calculations for Earth. And if you can remember, the Earth's F value is equal to 0.72. And Mars's F value is equal to 0.24. And the line between these 2 points shows where you should look on this particular date to see the planet from the Earth. And this parallel line from the Sun shows where the planet should be in the ecliptic. And as you can see, the celestial longitude of Mars is equal to around 121. And you can check if your calculations were correct just by going to the website called Your Sky webpage. And I have the results from this set website. And here's our Mars. And as you can see, the results are in pretty good agreement. Now let's move on to the concept of zodiac. The zodiac is 12-part division of the sky in the neighborhood of the ecliptic. We can imagine this as a wide band stretched around the celestial sphere and cut in half by the orbit of the sun. In astrology, these 12 parts are called signs. Each of these parts has a size of 30 degrees. And it's an easy calculations because 30 multiplied by 12 is 360, and it's a whole circle. As the sun makes its annual path around the ecliptic, it resides in each of these 12 signs. An individual born during a certain time would take on the sign the sun is in at the moment. The individual is then supposed to take on the characteristic associated with the sign. These characteristics are based mainly on some statistical studies and does not have to be 100% correct. For example, Edita and I are both Virgos, but we couldn't be more different from each other. And it is strongly connected to the house division, about which Edita will tell you.
So another important issue about which we would like to talk is the house division. Due to the slow movement of zodiac, a horoscope drawn up during a certain time would be valid for all people born around that time. The only character of it would be absent. Hence, in order to make astrology more personal, a local element was introduced to the cosmic elements. And this local element is called house division. The sky is divided into 12 parts, which are called houses. These whole parts are called houses. And usually the horizon divides them again, and half of them will be above the horizon and the other half will be below the horizon. The lines separating the houses are called cusps. So these whole lines are just cusps. Each house covers a specific area of light called spheres of light. There are several methods of house division, and I would like to show that geometry has its uses in house division, for example, in the equi-house system, which based on a division of the ecliptic. And this is a method of house division that divides each of 12 houses into equal 30-degree segments, starting from the degree of the ascendant, so from this point. And in this case, the ascendant is located at 15-degree Cancer. So the first house is between 15-degree Cancer and 15-degree Leo. This is the first house. And this area between 15-degree Leo and 15-degree Virgo becomes the second house. So this area, and so on. And in this type of division, medium Caeli, which means literally the point in the middle of heavens, floats freely in the upper half of the chart and does not determine the cusp or starting point of the 10th house, so this one house. But in this system, the 10th house always starts exactly 19 degrees before the ascendant. So here we have always an angle of 90 degrees. And what is also interesting, I would like to explain why people who have the same sign can have a little bit different nature. Like Agata already said, individuals should adapt the characteristics that are associated with the position of the sun above the earth. However, there are certain differences of houses during the course of the day. And seen from the earth, the celestial sphere rotates one on its axis during the day, and the ecliptic turns together with the celestial sphere. The ecliptic is the annual path of the sun with respect to the stars, And as a result, the size of houses is changing also during the day for a given latitude. Last topic about which we would like to talk is another type of divination closely related to numbers. There is belief in sacred or mystical connection between a number and one or more converging events, which is called numerology. I would like to present how numbers can influence our career. Two important issues which must be discussed in the context of numerology are birth number and the life path number. And there is no need to be an astrologer to get to know your birth number or your life path number. So, birth number is the single-digit sum of your day number, which is the day you were born. For example, if your day of birth is 14, your birth number is 5. We must add 1 to 4, and then the result is, of course, 5. And people with number 5 are smart workers and also multi-talented. They can opt for careers in, for example, law, journalism, music, or even acting. The second number connected with numerology, the life path number, is the one-digit sum of your full date of birth. And for example, someone who was born on 15 May 2000 must add up the numbers, so 1 plus 5 plus 5 and plus 2, and the result is 13. We of course omit 0, but then in the resulting number we must add the digits together. So for example, in this case 1 plus 3, and the result will be 4. And people with number 4 are multi-talented, but they can only make money through hard work.
And in conclusion, astrology uses maths to cast horoscopes or define one's zodiac signs. And to answer the question from the title of our presentation, I'll just say no, it's not possible to predict one's future 100% correctly based only on mathematics. In fact, most of the astrologers don't even use any maths at all, and they're just guessing or using some statistics. To cast a horoscope properly, they would have to be able to mathematically rotate the heavens back to the person's birth date, down to every second. And it will require lots of knowledge, not only in terms of mathematics, but also celestial mechanics. And at the end, we would like to present our bibliography and the sources we used. And thank you for your attention. If you have any questions, feel free to ask them now.
Thank you, all of you, for a very passionate and interesting presentation. Yes, let's check if there will be some question in the chat.
Yeah, because we are a bit late, so maybe if you have a question, feel free to ask them in the chat, but we will pass to the last lecture.
Yeah.
So yeah.
Thank you.
It would be really lovely to help the Earth using your mathematical skills. You could have some precise data, some differences, some reasonable arguments to take care of the climate change. And lucky us, someone has just done it. So we invite our last lecturer, Karolina Przybysz from Łódź University of Technology, who will show us that climate change is not an abstraction, but it's a truly big issue that we all should be aware of and try to handle. Big applause for Karolina. We hope now you can start.
Hello.
Hello.
Hello, we can hear you now.
Okay, perfect. You see the presentation? Is it changing? It is. Okay, so hello everyone. My name is Karolina Przybysz, and today I will present you with the mathematics of the climate change. Climate change is probably one of the most dangerous threats to the environment, our future, and the world economy. That topic has been present for a while on the lips of the scientists, but not too many people and governments seem to care for a long time. I have seen more climate denialism and greenwashing than bold actions and real plans to actually fight it, and now our planet is already about 1 degree Celsius warmer than it has been before the pre-industrial era, and according to the predictions, it will only get worse. But how is that connected to mathematics? Well, similar to the case of the plant that is withering because it does not have enough water, our planet is also in some fashion communicating its state back to us. We can understand it by the mathematics, which is the universal language of nature. Mathematics can address the climate change causes and effects by creating trackable equations, mathematical models, and analyzing statistical data. I believe that the sustainability of the planet Earth depends on the natural, engineering, and mathematical sciences, and wise people that will pursue it and communicate to the rest of the world what is going on, what has to be done, and what our planet will look like if we will do nothing. I would like to start my climate change considerations with the problem of the increasing content of the carbon dioxide in our atmosphere. It is a greenhouse gas which is released through the human activities such as burning fossil fuels, as well as natural processes such as respiration. Nowadays, the level of the carbon dioxide is bigger than ever in the last 800,000 years. The growth of that value started in the Industrial Revolution era, when we started to power almost everything with fossil fuels. In the year 1950, there were 3 times fewer people in the world than it is today. That year, we surpassed the level of the 300 parts per million of the CO2 in our atmosphere, and that value is skyrocketing ever since. The growing trend was gradual through the last years. In the presented period, every year, there was an average growth of the 2.322 parts per million of the CO2 in the air. That means that we have introduced the additional 34.83 parts per million of the CO2 in the last 15 years, and it will not stop here. Some people are still not convinced is that the human fault and claim it is just natural. Is it though? Let's check it with the mathematics. I will try to show that burning fossil fuels do increase the CO2 levels in the atmosphere. I have gathered data about the fossil fuels consumption in the 2010, and I took coal under the consideration as it is one of the most dangerous fossil fuels, responsible single-handedly for a 0.3 degrees Celsius increase in the world mean temperature amplitude. Using a stoichiometric equation, I have calculated how much carbon dioxide was produced by burning 7.282 billion tons of coal with assumed 35% of the carbon content. It turned out to be 9.33 billion tons of the CO2 emitted into our atmosphere. To calculate the parts per million of the CO2 in the atmosphere, I have researched mass of our atmosphere. I have created a proportion of the emitted CO2 to the mass of the atmosphere, including the fact that burning the coal took away a small fraction of the atmospheric mass. The output of that calculation was that coal added 1.82 parts per million of the CO2 into our atmosphere just in 2010. Since there are a lot of more fossil fuels than only coal, which was 36.94% of the all burned fossil fuels in the 2010, I have calculated that humans overall introduced 2.91 parts per million of the CO2 in the 2010 just from that action. Knowing that 58% of that will be drawn down by the ocean, plankton, algae, plants, and soil, we have been left with the 2.06 additional parts per million of the CO2 in the air we breathe in. Burning fossil fuels, each year we create more CO2 than the Earth can process, and that is causing that year by year increasing tendency in the carbon content in the air. Now let us compare that to the official data. National Oceanic and Atmospheric Administration reported that in the 2010, mean carbon dioxide growth rate was 2.3 parts per million. From our equation, 89% of the global CO2 growth rate from fossil fuels is 2.06 parts per million, so total growth rate is 2.32 parts per million. Close enough. The relative error is only 0.87%, which is quite good since I did a lot of simplifications in my calculations. And so that I can conclude that the burning of the fossil fuels indeed is the significant cause of the carbon dioxide content increase in our atmosphere. Now I would like to move forward and examine the different feature of the climate change, namely the rise of the global mean temperature difference. According to the data, the global mean temperature amplitude rises and it will maintain that tendency. Some of the predictions estimate that by the beginning of the 22nd century, temperature amplitude will be somewhere between 2 degrees Celsius to even 5 degrees in a worst case scenario. Generally, the 2 degrees is claimed to be a tipping point of a global warming. The meaning of it is that if we will surpass that value, our climate will be shattered, it will be causing more critical and less predictable changes that will be abrupt, irreversible, and will lead to a cascading effects of a natural disasters on a world scale. It is possible to foresee mentioned different climate scenarios by the means of the mathematical models. They can be really simple and intuitive, and they can grow into complex multivariable comprehensive climate models that can be supported by simulations and can be a starting point for future changes. As the example of the mathematical model, here we can see the basic mathematical Euler model, which is a system of partial differential equations with some lovely gradients and thermodynamic equation that describe the weather. It can narrate and foresee the important features of that so that we can decide if it is a good day for an outside barbecue or not. But weather is not the climate yet. To describe the climate, we should additionally consider things like ice sheets, ocean currents, vegetation, greenhouse gases, plankton, and much, much more. So now I would like to show you the simplest type of the mathematical model for climate change research. It is an energy balance model and it is very simplified, but it is astonishing how much we can understand from it. We assume that in that model, our planet is a single body with a single mean temperature T. In that model, the sun delivers the heat by radiation to our planet, and then Earth reflects some of that heat into the space. We can describe it with a simple equation where the heat radiated from sun is equal to the emissivity, which is an indicator of how much energy is radiated back from Earth to space, times Boltzmann constant, times Earth mean temperature to the power of 4. And this is equal to the absorbed heat, that is 1 minus albedo, that tells us how good Earth is in the reflecting sun rays, multiplies by the solar heating S. Having all of that needed values for our planet except from the temperature, we can calculate it by the Ricci arrangement of our equation as follows. From that, we have obtained that our planet mean temperature should be 14.85 degrees Celsius. And now let's come back for a second to our divagations about the CO2 and temperatures, because that equation connects those two features through the greenhouse effect. If the content of the CO2 and other greenhouse gases like methane or refrigerant gases is increasing, then the emissivity of the planet decreases, so less energy is radiated back into the space. In other words, they stop some of the heat from going out of the atmosphere, so intuitively the planet is getting warmer. Looking at the equation, we can confirm that, because emissivity is in the denominator, and as that value decreases, the whole fraction will increase, so that it causes increase in the mean temperature of the Earth. And now we can take a look at the graph of the CO2 content in the atmosphere on top of the global temperature graph through the years. And our modeled outcomes match perfectly with the data presented on the graph. So indeed, the temperature amplitude race is connected to the race of the CO2 in our atmosphere, and we have proven it by both mathematical model and statistics. So as we already know a lot about the causes of climate change, let's talk about the imminent consequences of it. Our planet is not a uniform ball like in our model. We have oceans that are getting warmer and more acidic as they draw down a lot more carbon dioxide than they are used to, which harms oceanic biodiversity. Ice sheets on Antarctica and Greenland are melting. We lose Arctic sea ice at the rate of almost 13% per decade. And if we will maintain that trend, there is a possibility that we will see the Arctic Sea without ice, with our own ice someday. And as a consequence of that, sea levels are rising, and in the future can deprive millions of people of homes. Moreover, we can expect more extreme weather events like hurricanes, storms, floods, and extreme heat waves followed by droughts. So what we should be doing as engineers and scientists to try to fight the climate change? First of all, I recommend the transformation of the energy sector and better diversification of the energy sources profile, in which renewable sources of energy should have a fair portion. As engineers, we can help to develop better technologies and make them more efficient and more cost-effective. Also, we should strive to ensure the higher energy efficiency and design devices that are less power hungry. We can engage ourselves in the projects and create sustainable technologies for the actual needs, like technologies to conserve and protect water resources. Also, we can learn how to create new and better mathematical models to kick into the efforts of the scientific circles and present arguments to the public opinion and institutions. And most important in the end, we have to educate ourselves by cultivating lifelong learning and teaching others. It is necessary to bring the topic of the climate change into the education to prepare us and the future generations to understand and prepare for changes. Sometimes it is just enough to talk about it. Ensure the free flow of the ideas and inspirations in your life. Let other people know what you think, because your points for sure are valid, and have the audacity to change the world. Here you can see some of the resources I used to prepare the presentation. You can contact me if you are interested to read or listen more about that topic. Thank you very much for your attention. Now I would gladly answer your questions.
Thank you, Carolina. You have undertaken a really difficult and important matter, but you handled it great. So thank you so much again, and we will be happy to have listened to your lecture.
Thank you very
anyone
much.
has questions, please ask them in the chat box, or by email, of course. And now we would like to say a few words one more time about the patronage. The patronage, yeah.
Yes, exactly. So once more, our conference is under the honorary patronage of the Ministry of Education and Science, the headmaster of the City Łódź, Parlament Studentów Rzeczypospolitej Polskiej, as well as the patronage of His Magnificence Director of Łódź University of Technology.
And Association of Women in Technology, and of course the media patronage such as Polish Television, Student Radio Żak, and Życie Uczelni. Okay, so we have one thing for you yet. A quiz, like can
Be
you tell
patient.
us? Yeah.
1 second.
Yes, so you can see here the QR codes for the quiz from today's presentations, and some voting platform to vote for the best presentation, and that will next be given the award for this person.
Yes. Now you will have, I think, 15 minutes for this part. So the best presentation, choose wisely who was the best in your opinion, and also the other for the quizzes from the question from our
lecturers.
Exactly.
Someone's writing.
There will be a link in the chat also in a second.
Yes.
Okay, so in the meantime of our quiz and voting for the best presenters, we would like to thank our presenters and all our guests who take part in this conference. We hope that you heard quite passionate presentation and that you learned something new, and it maybe forced you slightly to discover new topics and new things and aspects which can be combined with mathematics in your everyday life. And we would like to invite you for the next day, so Tuesday, 5th April, for the Polish conference meetup, which will be conducted in Polish, but even though there will be quite many interesting presentations and prelegents, and we hope to see you again next days. Yes, there will be a link in a second.
You can also use the QR codes, they should work properly, so maybe that way will be faster.
Please wait a second, the link should be soon in the chat, but you can use the QR code, which we
They are
check by ourselves, and it works.
Well, mhm. So we hope you succeed in doing the quiz and the voting part by the QR codes, because as we said, we have some issue with the links, but still, we hope that you enjoyed our presentations and that this was a valuable experience for you, and we invite you for tomorrow and after tomorrow for a Polish part of this MathUp conference. Goodbye and see you again.
Goodbye.